Hello, my name is Kaia Gray, and this summer I was able to do research at the University of Pittsburgh thanks to the NIH SenNet program. We studied cellular senescence with respect to COPD and IPF. First, when we talk about senescent cells, we want to talk about aging and what characterizes aging. That is decreased organ and metabolic function, poor memory, worsened immune system, and social burdens such as aiding to the sick and finding places to live, such as nursing homes. But with aging, we'll specifically look at lung function and elasticity and how they deteriorate over time. When we look at the schematic on the right, we see that with age comes an increased amount of senescent markers and increased inflammation. Some age-related diseases we'll be looking at is COPD and IPF. COPD is chronic obstructive pulmonary disease. Those who are smokers are at higher risk. However, 30% of those diagnosed aren't smokers. This is characterized by emphysema and chronic bronchitis. IPF, or idiopathic pulmonary fibrosis, those who are smokers are also at higher risk, but if you have a family history and if you're an older adult, you are susceptible. This is characterized by damage and stiff alveoli, and because the tissue becomes so damaged over time, it becomes fibrotic. What is cellular senescence? Because cellular senescence is characterized by age, it is a hallmark of aging. It is characterized by an arrest in the cell cycle that stops proliferation, but the cells do not die. These cells enter the state of senescence due to internal and external factors such as DNA damage, telomere shortening, oxidative stress, and some biomarkers that are associated are P21, P16, P53, and P19. And a secretome SASP is also released, which we'll talk about in the next slide. And inflammation is a large factor of senescence, and we'll also get into why that's important. So how do we identify these cells? There isn't a one way to identify or look at a cell and know that it's senescence, but we do have different biomarkers that we will look at. Specifically, we'll look at P21, SA beta gal, and SASP. What SASP is senescence-associated secretory phenotype. It has both negative and positive effects. It can aid in proliferation and regeneration, but it can also cause inflammation and damage to tissues. So we hypothesized that the loss of mitochondrial transcription factor A would induce cellular senescence in lung epithelial cells because TFAM is a regulator of mitochondrial biogenesis. It would induce mitochondrial dysfunction and cause senescence. Our second hypothesis is that the senescence of epithelial cells may promote proliferation of fibroblasts via SASP. And our method of getting rid of TFAM is through this this gene sequence we have right here. We have LOXP, TFAM, and LOXP. So when we inject a virus that contains CRE, the CRE recombinant will bind with LOXP, and when it binds, it will delete TFAM and combine to just LOXP. So to induce this, we did use a virus, and we used it with the we used primary cells from a TFAM LOXP mouse, and we isolated the cells thanks to Ugochi, our lab tech, and we got AT2 cells. And with these primary cells, we injected the virus containing CRE. And this top line right here, we see that it's adeno EGFP, and that is going to be CRE negative, meaning the CRE does not work, and the TFAM will still be there, so there will still be mitochondrial function. And the bottom, we see that it is CRE positive, so the CRE will get rid of the TFAM. And on days 3 and 7, days post-infection, we will collect the supernatant and see if SASP is in the supernatant. So we will identify the senescent cells using SA beta gal staining and immunofluorescence staining of P21. So senescence-associated beta-galactosidase staining is used as a biomarker of senescent cells. However, all cells do contain beta-gal. It can be found in normal and senescent cells. So what makes this staining so important is that it's at the pH of 6, which is where we can find senescent cells only. Now, when we look at our graphs and data, we see 3 days post-infection. At the top is Cre negative, meaning that Cre did not knock out TFAM and is still mitochondrial function. And we see that there's barely any blue staining that indicates that there are senescent cells. At this graph, we see that it's less than 10%. Then we look at Cre positive and we do see more blue staining, and we see it's a little bit over 40%. Then we go to 7 days post-infection and we do see a little bit of blue in Cre negative. However, the cells did become confluent. So when it does become that full, cells do tend to enter the senescent state, which is why you see it is a little bit over 20%. But when we look at Cre positive, we do see an increase in possible senescent cells with a little bit under 60%. We also did immunofluorescence staining of P21, and we used the indirect method, which gives us a stronger wave and stronger signal. So what we do is we take a primary antibody and we attach it to an antigen. Then we take a secondary antibody and we attach it to the primary antibody. And on that secondary antibody, it's a fluorophore that emits light. And we use it to attach to certain structures of the cell. So we use it to attach to P21 and to the cell nucleus. So this is an example of immunofluorescence staining, and this is for P21 once again. And the top Cre negative with DAPI, the DAPI is the blue staining that shows the cell nucleus, and the purple or pink staining you see here is of P21. So we see that Cre negative versus Cre positive, there are more P21 cells in Cre positive. And we can see at this graph that there's a little bit under 30% and then a little bit under 10%. And then we go to 7 days post-infection and we do see an increase in P21 cells. And that is a great indicator that the knockout of TFAM was able to induce senescence. So summary, once again, we see that TFAM knockout can induce epithelial senescence. And the next steps is to see whether the SAS secretome from senescent epithelial cells can promote proliferation of fibroblast cells, which was our second part to the hypothesis. So in order to see if the cells can proliferate and migrate, we do a scratch assay. And once again, this shows whether the cell can migrate and proliferate. And in order to do a scratch assay, first we have a confluent cell, confluent well, and we make a line, and this line is made so we can look at it over a certain amount of hours. So in this example, it was 8 hours. And if we see an increase in density or we see a closing in that gap, then we know that the cells were able to proliferate and migrate. Now with this, we used the supernatant from the TFAM knockout cells that we hope would have SAS secretome in it, and hoping the SAS secretome would be able to cause proliferation. And we used the CCL206 cells, and this is a cell line of long fibroblasts from mice cells. And we hope to see that it did cause proliferation. So the workflow, how we did this, we seeded the cells in the well. Then over the 12 hours, we attached it. Then after that time, we starved the cell by using 0.1% FBS. And this is just a lower amount of nutrients in the media, so we can get the cells to kind of be on the same cell cycle. And then after that, we did a treatment. which was the secretome and imaging. So this is only one replicate of the Scratch essay, and it's also, I wouldn't say it's the best data because the cells did detach from the cell well, from the glass bottom of the cell well, but we were still able to look at the density of the cells. So we see over time that when we look at this graph, that there was an increase in density for the respective days. So 7 days post-infection CRE positive and 7 days post-infection CRE negative. We do see that there's an increase in CRE positive. However, it's small, but I would say we would do another replicate to get more steady results. But we do see a change in the gap when we look across from left to right. So once again, the next steps would be to replicate this cell scratch assay, and the outlook for what I think should possibly be done next is we should identify the SAS biomarkers such as IL-6 and IL-8 and their function. Because SASP can have both positive and negative effects, I think it's very important to look at these specific biomarkers and see if they cause reactions that are positive or negative. And lastly, I would like to say thank you to CUSP and to the NIH SenNet Consortium for allowing me to have this opportunity, and my mentors, Melanie, QJ, and the Pink and Blue Lab for all their help, for giving me this opportunity to study and to grow as a person and a scientist. And I'm really appreciative of everything that has been done for me. Thank you.